Hello everyone, thanks for joining me for this quick poster presentation. I'm Pauline Chevalier from the Department of Molecular Pharmacochemistry of the Grenoble University, and I'm going to present you the work related to my PhD project, developing an aptamer-based assay to detect and quantify a specific microorganism. This project aims to answer a major public health issue, which is the management of bacterial infectious disease and the control of the spread in the population. This is even more essential considering the emergence of multi-resistant bacteria. However, current culture-based reference methods are time-consuming with a turnaround time around 24 to 72 hours, which is highly incompatible with if the diagnosis is of vital importance. In that context, our aim is to propose a complementary detection tool to overcome the deficiency of the reference method. The project is divided in 3 steps. First, the microorganism of interest is specifically recognized by an Aptamer sequence. Then, in order to concentrate and extract the microorganism, the Aptamer is coupled to a solid support that can be secondarily isolated from the contaminated sample. And finally, a quantification method such as flow cytometry can be implemented. For the proof of concept, an Escherichia coli 157H7 strain was chosen as target. This serotype is widely described as responsible for foodborne illness, therefore there are diagnostic interests in targeting it. Other E. coli strains were used as control. An Acinetobacter baumannii strain was used as gram-negative control, and Streptococcus pneumoniae and Staphylococcus epidermidis strains were used as gram-positive controls. The first step of the project was dedicated to the identification of the specific Aptamer sequence against E. coli from the literature. In that context, the Aptamer APTA1 was selected from the bibliographic study to perform tests. In order to verify the specificity of the Aptamer sequence, a scrambled sequence was randomly generated from the chosen sequence APTA1. To assess the interaction between the Aptamer and the bacteria, a flow cytometry-based method was developed. The fluorophore-tagged Aptamer is incubated with the bacteria of interest during a certain duration, and the sample is then directly analyzed with the flow cytometer. The bacterial suspension goes through a laser, and bacteria are sorted according to size and fluorescence. Then, fluorescent Aptamer-labeled bacteria can therefore be discriminated from unlabeled bacteria. And if you want to have more detail about this method, I invite you to see my colleague Juliette Nouri poster 23. Here are the results of the Aptamer-based test implemented for bacterial identification. First, the comparative analysis of APTA1 and its scrambled sequence on the E. coli 157H7. The result given by this graph cannot allow us to conclude about the specificity of the sequence in the tested condition. Then, the comparative analysis of the interaction between APTA1 and various strains. And the results suggest a potential specificity for gram-negative bacteria from 10 to 15 nanomolar. Based on this result, we decided to test a fluorescent antibody to validate the method. So the same test was performed with an anti-157 antibody. And this time, the specificity against the E. coli 157H7 was clearly demonstrated. To conclude this presentation, we tried to reproduce literature results, and even if we have obtained similar results, the specificity tests with the scramble were inconclusive. So we are quite disconcerted by the complexity of identifying an Aptamer sequence for the detection of whole cell bacteria. And we are still searching for the good sequence for this project. I hope this work has piqued your curiosity, and I would like to thank you for your attention.